Hi, this is a PowerPoint video about computer chips, also known as microchips or semiconductors. What are they? Why are they important? How do they work? How are they made? And who makes them? And you're going to see that these chips are in a lot of the devices that we use in life. First of all, what is a microchip? It's a set of, It's a set of electronic circuits on a small flat piece of silicon. Looks like this, very small. Micro means small in Greek, right? A microchip is also known as a chip, a computer chip, or an integrated circuit, an IC, or a semiconductor, or a semi. So these are all terms for the same thing. Why are these chips important? These chips power our computers, our smartphones, cars, appliances like washers and dryers, refrigerators and microwaves, and scores of other electronics. Absolutely essential to our lives. For example, cell phones use many chips. So here you can see all the different chips that are in the Apple iPhone. Okay, some are made by Broadcom, Texas Instruments. Okay, these are huge, huge companies. Apple, Qualcomm, Broadcom, lots of chips. This is the inside of a cell phone, and you can see the chips in black, and they are put onto these motherboards, okay? The chips are sewn. You can see the little grips or attachments. They're sewn onto the green motherboard, and this is how our electronics work. Here's a close-up. Okay, in black, this rectangle, this square, these are the chips, and they're held onto the green motherboard, and you can see these little metal connections. This is how electronics work. For example, video game consoles depend on chips. Here's the motherboard of an Xbox, and you can see some memory chips in black. Here's a logic chip, and this is a DAO chip. Okay, there's several different kinds of chips, all on this green motherboard. Cars also use chips. It's a chip that triggers your airbag or your cameras. Okay, lots and lots of computers in our cars, and the average car is packed with 1,400 semiconductors. There are also chips in our household appliances, washers, dryers, okay, refrigerators, in our health equipment like ultrasound, x-rays, ventilators. So do we need chips? Yes or no? Why or why not? How do chips work? Well, first of all, remember everything's made up of an atom, and we're going to get into science here, a little bit of chemistry. And remember that there are these electrons that float around the nucleus of an atom, and these electrons have a negative charge. Okay, so when electrons move, they carry electrical energy, and that steady flow of electrons is called an electrical current. And for an electrical current to happen, you need a circuit. A circuit is a closed path or loop that the current flows around. And a circuit is made up by linking different parts together. What are the parts that make up an electrical circuit? Well, first of all, you need to push the electrons to get them flowing. And that push or voltage is measured in volts. And the push or voltage comes from a capacitor or a battery. So we're going to get a little bit into science for a second, okay? A capacitor, the way to make that is you put an insulator, which does not carry electricity, in between two conductors. And conductors are materials that do carry electricity, okay? So you really have two types here, a battery and a capacitor. A capacitor releases energy very quickly. For example, a camera's flash, a flash bulb, that comes from a capacitor. But a battery releases energy very slowly over time. So again, capacitors push the electrons. This is what capacitors look like in reality. They're really small. Here it is sewn onto a motherboard, and they push the electrons to get the electricity flowing. This is the symbol for a capacitor. This is a symbol for a battery. Again, batteries release the electrons slowly. Capacitors release them quickly, like a flash bulb. After pushing the electrons, you need to get them to go where you want them to go. How do you do that? You can control the flow of electrons by sending them along conductors. Those are materials, they're metals like copper, and they carry electricity very well. Okay? You can also use resistors. Resistors do not carry electricity, so you can use the resistors to limit the flow of electrical current. Okay, so when electrical energy passes through a resistor, the energy is turned into heat and light. For example, in a light bulb, a metal, in this case tungsten, acts as a resistor. And when the electricity passes through it, it heats up and it lights up. So you can have your electricity flow through these conductors. The electrons flow very nicely, but then it goes through a resistor like tungsten. It's kind of metal, and as the electrons go through, it heats up and it lights up. Here's the symbol for a conductor. Like copper, it's a metal, the electrons flow very nicely, and these are the symbols for resistors, and when the electrons flow through there, it heats up and it lights up. So some materials carry or conduct electricity well. Those materials are called conductors. For example, metals, especially copper. Okay, you can see them over here, copper, aluminum, these metals. The electrons flow down those pipes or cables very nicely. Other materials do not conduct or carry electricity well, and those materials are called insulators. Okay, and here you can see some wood, glass, rubber. Electricity does not really pass through those. Okay, and then you get materials that are kind of in the middle. They do a so-so job of conducting or leading the electrons, and those are called semiconductors, right? Semi is half. So these are kind of sort of half and half good at letting the electrons flow through. And a great famous example of a semiconductor is silicon. Again, different materials have different properties. For example, you know not to touch a hot metal pan with your bare hands because the metal conducts heat. Ouch, you're going to burn yourself. But it's okay to touch this handle because it's coated with rubber. Rubber is an insulator, okay, or a resistor, so it does not conduct well. So different materials have different properties. Copper is great at conducting heat and electrons and electricity. Wood, rubber, glass, not that great. Those are insulators. And then sort of in the middle, half and half, you have your semiconductors, like silicon. So often, copper is the conductor and plastic is the insulator. So you get a conducting copper wire, and the electrons and electricity are flowing down through that, and that is wrapped around a plastic cable that you and I can touch, and we will not get an electric shock. Computer chips are made out of silicon. That's, again, a material that does a medium, sort of so-so job of conducting and insulating, and so we call silicon a semiconductor. And that's why silicon computer chips are also known as semiconductors or semis. So here's the element that we might find in nature, okay? And the silicon for a chip has got to be very pure, 99.99% pure. It's called 99 silicon, very pure, so that the electrons will flow down through it in a pretty good way. And we turn this silicon into a rod or cylinder. Okay, so here's the diagram of a simple light bulb circuit. So here we have the battery that's slowly releasing the electrons, pushing them out, and they flow on this copper wire, okay? And here we go. Here's the battery, slowly letting it flow through, okay? And then it gets to a resistor, okay, like tungsten, and it heats up and it lights up and it gives off heat and light, and then the electrons continue to flow through their way. So this is a simple circuit, a simple loop. Another important part of a circuit is a transistor, and transistors can be amplifiers or they can be switches. An amplifier turns a small electrical current into a much larger one. For example, hearing aids, microphones, and loudspeakers. And another kind of transistor is a switch. Switches can be on, and then the current of electrons flows, or switches can be off, and then there's no flow. All right, this is what it looks like. Okay, so your electrons can come in through the collector. This is the collector. The electrons could flow in, and then this transistor can be on or off. If it's on, the electrons are going to flow back out through this E or emitter. And if the transistor is turned off, the electrons don't flow. So here's another diagram of a circuit or loop. Here is your battery, okay, and it's pushing the electrons out. And here is your transistor, okay, and that can be on or that can be off. If your transistor's on, the electrons will flow, and for example, you can power that buzzer. Here it is again. Here's our battery. The battery pushes the electrons out, and it flows through this switch, this transistor, and if you switch it on, then the electrons will continue to flow, and it lights up this light bulb. Just one circuit can, for example, turn on a light bulb. Many circuits can, for example, light many light bulbs, and then, for example, you could spell out a name, like here's Elvis, the famous rock and roll musician. The more circuits you have, the more complicated stuff you can do. And our computer chips have millions of tiny, tiny circuits on them. And since electrons have very, very, very little mass, they move really quickly, and so computer chips can do things very quickly, because again, they have millions of circuits with millions of electrons. They're flowing very quickly, so you can get a lot done very, very quickly. All right, let's do some history and talk about the development of these chips. In 1958, in Texas, this guy, Jack Kilby, wanted to make circuits smaller. This kind of a circuit with a battery and a light bulb, that's way too big. He wanted to make them smaller. So he put the parts, the transistor and the capacitor and the wires and all that, he put these parts and he made them out of silicon, and he put them on a chip, and it was all together, and so it's called an integrated circuit, or an IC, all on a chip. And he did this in Texas, and this became Texas Instruments, and that powers those famous TI calculators. So here is an integrated circuit, or what we would call a chip, because it's small, it looks like a little chip. It's got a capacitor on there, it's got resistors, it's got transistors, it's got millions of those little circuits, millions of those little loops. Then in 1959 in California, Bob Noyce was working, and he realized that a whole circuit could be made on a single chip. Okay, so these two people, Jack Kilby and Bob Noyce, are known as the fathers of the microchip. How do we make these integrated circuits today? How do we make chips today? Again, we start with a very pure rod of silicon, 99.99% pure, and we slice it and cut it into these thin silicon discs called wafers. And then what we do is we add chemicals to the wafers, things like antimony, boron. I think boron is a gas, and it makes the silicon metal act differently. So here you take your pure silicon, you bathe it in boron gas, you can add antimony, you can bathe it in phosphorus gas, and these chemicals change the properties of the silicon metal a little bit. For example, part of your silicon wafer is bathed and gets chemicals added to it, boron, antimony, that kind of thing, and that's the N-doped part. It's doped in a certain way, treated in a certain way. Another part is called P-doped, and so when you add an electron flow to it, the electrons will flow, and it's like a pipe, it's like a conductor. It does just what you want it to do. It's a little bit like making a road. To make cars go where we want, We lay down asphalt and we make a road. The cars stay on the road. They don't go over here on the grass. They don't go over here. The cars stay on the road. Similarly, to make electrons go where we want, we put boron, antimony, phosphorus on a silicon wafer. And then we shine a light on it. It's like carving a path. And the electrons stay on the path just like the cars stay on the road. So here's the next step. We're going to shine light through a mask, through a filter, and it's going to kind of burn and etch away these roads, okay? And that's going to create the pathways we want so the electrons are going to flow, okay? You can also burn it with acid and light. And so it's called photolithography. Photo is Greek for light, and lith is the stone, because we're basically carving on this silicon metal, and graphy means writing. So again, we shine this light source through this mask, and it like carves pathways onto the chip. This is what a photolithography machine looks like today. They cost hundreds of millions of dollars, and they are incredibly expensive. And they carve these tiny, tiny pathways onto these silicon wafers, and they make a lot of chips. So here you see a silicon wafer with all these chips. They've been bathed with boron and phosphorus and antimony, and we used light to carve pathways. Here's a close-up. And then we cut up those chips, and again, we sew it onto the motherboard, and that goes into your cell phone. Just one piece of chip, just one piece of dust can ruin the chip because it interferes with the light. So chip factories, which are known as fabs, it's a fabrication facility, they have to be cleaner than a hospital room. They need very complex systems to filter the air, regulate the temperature and humidity, because again, just a piece of dust can mess up the whole operation. So this is a fab, this is a factory, and they have what are called clean rooms. And they have to be 1,000 times cleaner than a hospital operating room. And again, these people are in special outfits because if one of their human hairs comes out and falls on the chip, it's going to mess it up. In other words, this is incredibly complicated. This is how we make the chips for your cell phone, for your car. It is very hard to build a factory, also known as a fab. You can't have any vibrations that will cause the equipment to malfunction. So these fabricatory clean rooms are built on enormous concrete slabs on special shock absorbers. They also have giant fans to circulate the air. They have pumps, they have pipes, they have chillers to maintain a consistent temperature. It is unbelievable. Here are the big air ducts and the fans that carry the gases away. This has got to be incredibly, incredibly controlled. Building a new fabricatory costs about $20 billion in several years to build. So this is Intel. Intel's a big company, and here's some of their fabs in Chandler, Arizona. This is near Phoenix. So this is like a $20 billion building. The end result is, again, a chip, an IC, an integrated circuit, also known as a semi. Millions of circuits carved onto one chip, and you can see it's smaller than your fingertip. We have different types of chips. We have digital chips, and they receive an electrical signal, so they're either on or they're off. You have analog chips, and they're used to measure real-world data, like temperature. Temperature isn't on or off. It's either 78 degrees or 75 degrees. Your heart rate isn't on or off. It's 116 beats per minute or 117 beats per minute, but it doesn't go off, hopefully. So you have analog chips that measure real-world signals, and you have mixed chips that can combine digital and analog. Chips also differ by function. Memory chips store data. Converter chips can convert signals. Amplifier chips amplify like a hearing aid. You have logic chips, CPUs, and GPUs. GPUs are graphic processing units, and that's what we use in video games. So, who are the largest makers of chips? Let's look at it by market capitalization. Market cap is how much capital, how much money has been invested in them. And you see today that NVIDIA is the largest chip maker in the world in terms of how much the company is worth. I think it's actually now $4 or $5 trillion. And what kind of chips does NVIDIA make? They make the chips for video games, and they make the chips for artificial intelligence. So those chips are in really high demand. TSMC is Taiwan Semiconductor Manufacturing Company. It's in Taiwan, off the coast of China. Incredibly important company. Samsung is in Korea, okay? And Texas Instruments is in Texas. These are incredibly important companies. Let's look at it now by revenue. Revenue, in other words, sales. Sales does not mean discounts. Sales and revenue is the money you make from selling products. Okay, so Samsung's Korean company. Okay, you see South Korea, they make a lot. Okay, and here you have TSMC in Taiwan. The United States has got Intel, AMD, Qualcomm, Broadcom. These are all major companies. ASML's in the Netherlands, and they make the machines that make the chips. We'll come back to ASML. It's one of the most important companies in the world. All right, you might have heard of Texas Instruments because you might have used a TI calculator. So here's a TI fab, or a fabrication factory in Texas. Again, here's Jack Kilby, who shrunk the circuits and put them all on a tiny chip, and this is the TI headquarters in Dallas, Texas. Very important electronics company. Here's Intel. All right, Intel was started by three giants, Robert Noyce, Gordon Moore, and Andy Grove. And here you can see one of their factories. This one's in Israel. Here's their headquarters in Santa Clara, California, just south of San Francisco. And the Intel chips are the CPUs. It's like the brain of your laptop. Okay, here it is. Here's an Intel chip. This one was made in Korea, but Intel's an American company, and it's sewn onto the motherboard. Samsung, huge company. Here's the headquarters in Seoul, Korea. All right, here's a fab or factory costing billions of dollars where they make the chips in the Samsung cell phones. And again, NVIDIA is now the largest company in the world. Okay, it has grown really quickly the last couple years. It makes chips for video games and chips for artificial intelligence. So if you look here, how do you think these companies have done over the last couple years? What's happened to their stock? I want to focus on Taiwan Semiconductor, TSMC, because it's one of the most important companies in the world. And it was started by Morris Chang. He was born and raised in China and Hong Kong. He went to Harvard and MIT to get his engineering degree, and he worked at Texas Instruments, and he got promoted. He wanted to be the CEO, the head of TI, but he felt he wouldn't. This was back in the 70s and 80s because he was Asian, and he wanted to run his own company. He knew that Taiwan's labor was cheaper than United States labor, but Taiwan engineers did not know how to design the chips. So he thought, I'll start a company that just makes the chips that are designed by other chip companies. So he started TSMC, and it is what we call a foundry. It just makes the chips. So Apple will send their chip design, Intel, Samsung will send their chip design to TSMC, and the TSMC fab or factory in Taiwan will make it. And it is arguably the most important company in the world because they make the chips that run our electronics. Okay? Our cell phones, our cars, our computers, our washers, our dryers, our microwaves. Again, TSMC does not design the chips, it just makes them. Okay? So it's called a foundry. And if you look at the market share, who's actually making the most chips, it's TSMC. TSMC makes about 2/3 of the world's chips. Okay, Samsung in South Korea also makes a lot. So here's TSMC, here's their headquarters, the office building, here's a fab, and they're located in Taiwan, okay, which is this country, an island right off the coast of China, okay? So it creates some geopolitical threats and uncertainty, because if war were to break out, then China might be able to take Taiwan quickly. And if China takes Taiwan, they take TSMC, they can control the manufacturing of chips, and they could maybe cut off the rest of the world, and the rest of the world could not have access to their electronics. So that could be a major, major problem. TSMC is one of the most important companies in the world. Another incredibly important company is ASML. ASML is a Dutch company. It's in the Netherlands, in Europe. Here's their headquarters, all right? And they make the machines that make the chips. So this is a photolithography machine. It costs hundreds of millions of dollars. It's incredibly complicated, okay? So these machines make the chips. The circuits, the width of the pathway now that the electron goes down is measured in nanometers. A nanometer is a billionth of a meter. So these are incredibly narrow pathways. And I'll give you an example of that. Today's chips have circuits, have pathways that are smaller than 10 nanometers. Well, how small is that? It's really small. A virus is 14 nanometers wide, okay? A strand of DNA is about 2 nanometers wide, okay? So this is just microscopic. Let's look at this, okay? A human blood cell is about 7,000 nanometers wide. A human hair is 50,000 nanometers wide. And these circuits are about 10 nanometers wide, okay? So they're more narrow than a virus. They're a lot more narrow than a blood cell or human hair, okay? It is unbelievable, okay? It is unbelievable. Shipping one of these photolithography machines, shipping one of these things with all the different pieces, takes about 40 freight containers, 3 cargo planes, and 20 trucks. Okay, these things are absolutely unbelievable, and these machines can carve pathways that are so thin. They are thinner than a red blood cell, thinner than a virus, thinner than your hair. Again, here's another picture of it. They use ultraviolet light now to carve it, okay? And just to give you an example, it's just unbelievable. There are vacuums in here, and they shine light and off a mirror, and the mirrors are unbelievably flat. Okay, and here you see this. This is just mind-blowing. There's a laser that shines a light. And this happens 50,000 times a second. So you get a really thin, narrow light beam or laser beam, and it can carve a really thin, narrow circuit. So again, this is unbelievable. The UV light that they now shine on the chips is so precise, so narrow, so thin, so fine, that they can carve more than 50 billion transistors or switches on one chip, okay? This is 10,000 times smaller than the width of a human hair. It's just mind-blowing. For example, one Apple M2 chip has 20 billion transistors on it. Remember, the transistors can turn on and off to let the electrons flow or not flow. So this is unbelievable, okay? So, to wrap this up, does this surprise you? Does this surprise you? This is the world's 50 most valuable companies. Saudi Aramco, big oil company. Visa is a big company. JP Morgan Chase is the largest bank in America. Lilly makes pharmaceutical drugs. So does Merck, Johnson & Johnson. These are huge companies. And who dominates today? It's a lot of these companies that are involved with chips: ASML, TSMC, NVIDIA, Apple. So I hope you understand this is absolutely essential to our lives and the world economy. If you have any questions, please let me know. Thank you.